Hello, everyone. Welcome to the first lab for Physics 206 and 207. So in this lab, basically what we're going to do is we're going to practice computing some measures of accuracy and precision. So something called the percent relative average absolute deviation and the percent experimental error. And then we're also going to practice a little bit with graphing. So doing some simple graphs using Pascal Capstone. So before performing this lab, make sure that you have read Appendix A and B from the lab manual. And I also posted some video lectures on how to draw good graphs and also how to compute those measures of accuracy and precision. Okay, so it's important that you already know that information. So this lab will just give you some practice on that. Okay, so the first part, part A, you're told that a meter stick was used to measure the length, width, and height of a physics book. Okay, 5 trials were performed for each measurement. So 5 trials for length, 5 trials for width, 5 trials for height. So using the data that I gave you in the table here, I want you to calculate the average length, the average width, and then the average height, and then their corresponding prads, right? So the percent relative average absolute deviation for the length, the percent relative average absolute deviation for the width, and then also for the height. Okay, so again, use the knowledge that you learned from Appendix A and B or from my video lecture on how to compute PRAD. One thing you should notice here is remember that the resolution of the instrument is important, right? So if you look at all the data that was given in the table here, these are all to 1 decimal place, right? Which means that the smallest length that could be measured by this meter stick was zero point 0.1 centimeters, right? Which is the same as 1 millimeter or zero point 0.1 centimeters. So that's the resolution. 0.1 centimeters would be the resolution of this instrument. Okay, so the first part again is find the averages and find the prads for length, width, and height. Oh, in fact, I kind of gave you this answer, right? So make sure you understand that the resolution of the meter stick should be 0.1 centimeters. Okay, next, you're told that the volume of a rectangular solid, right? So the volume of a box or of a book is given by length times width times height. So V volume equals length times width times height. Assume the book has a shape of a rectangular solid, and I want you to compute the volume of the book and then the prad for volume. Okay, so remember how to compute PRAD for the dependent variable um, that's equal to the product of a bunch of variables, right? So if you have an equation and you have several variables in that equation and you want to find PRAD for the dependent variable, remember there's a rule that you have to use. Actually, let me go to the tablet to explain this more carefully. Okay, so again, remember that the formula for the volume of a rectangular solid, which we're going to assume the book is in this case, is length times width times height. So to compute the volume of the book, you're literally just going to plug in your average length times your average width times your average height, right? And that'll be the answer in centimeters cubed. Okay, the other thing I wanted you to calculate was PRAD for volume. So we want to find PRAD. So the percent relative average absolute deviation for the volume of that book. So remember the rule, right? Whenever you have an equation that involves either multiplying variables, such as the case here, right, where we have length times width times height, or this is also true if you divide variables. Okay, in this case, we're just multiplying variables. So the rule is if I want to compute the PRAD for this dependent variable here for the volume, then I have to add the respective prads together. So the variables are multiplied or divided. You have to add their respective prads. So in this case, the answer would be the prad for length plus the prad for width plus the prad for height. And that will equal the prad for the volume. Okay, so once you find the prad for length, width, and height, which you have in the previous tables, right? You already computed those, just add those three percentages together, and that will be your prad for volume. Okay, part B. So part B, you're told that the diameter of a basketball is measured 10 times with a caliper that has a resolution of 0.01 centimeters. Using the data below, compute the average. So you want to find the average diameter and the prad for diameter. Okay, so here's your data. So again, notice that all these values here are to two decimal places, right? So that's why the resolution was 0.01 centimeters. That would be the smallest length that could be measured with this caliper. So again, I want you to compute the average. So the usual, right? Add these up, divide by 10, but make sure, this is important, make sure you round to the resolution of the instrument, which is two decimal places. By the way, back here, make sure that all these averages, right, when you found the length, width, and height of the book, make sure these are all averaged to one decimal place, right? Because that is the resolution. But for the diameter, you can round it to two places. Okay, then I want you to compute the prad for diameter. So you have, I gave you this column again with the absolute deviation, so you can find all of those, right? How far each value is away from your average, right? Remember, these are all going to be non-negative. Then you average these. Again, make sure you round to the resolution of the instrument, so two places. And then the prad is always going to be the average absolute deviation divided by your average diameter times 100, right? Just like you did up here for the length, width, and height. Okay, now we're told that the volume of a sphere is given as 4/3 pi r cubed. Okay, and we're going to treat a basketball to be a sphere, right? A perfect sphere. Now notice that we didn't really measure the radius, we measured the diameter. So I'd like to rewrite this formula in terms of the diameter instead of r. So and put it in terms of d instead of r. So we know the relationship between diameter and radius, right? Diameter is twice the radius, or you could write this as radius is half the diameter. So if I substitute in for r here, d over 2, right? Half of d. And if you expand this out, you're going to get 4/3 pi d cubed over 8. And then if you simplify, it turns out this is equal to 1/6 pi d cubed. Okay, so I want you to calculate the volume of the basketball. You're simply going to use this formula here, 1/6 pi d cubed. And for d, you're going to put in your average diameter value, whatever you got for your average here. Okay, what about the prad for volume? So this is similar to what we just saw, right? Um, in effect, we're multiplying the diameter three times. Okay. Again, let me jump over to the tablet to explain this more carefully. Okay, so again, the volume of a sphere, right, of the basketball is going to be 1/6 pi times the diameter cubed. When we want to calculate prad, right, we have to think of it this way. First of all, the 1/6 and the pi, those are exact numbers. They have no error. So you don't have to worry about them when you're computing prad. It's only the variable, right, the diameter that has error. And we already know the prad for diameter because we computed it. So the way to think about this is the volume here, I'm going to ignore the 1/6 and pi. So this is like proportional to diameter cubed, which we can write as d times d times d, right? That's what diameter cubes means. Diameter times diameter times diameter. And remember, the rule is if I want to calculate prad for the dependent variable, in this case, the volume, and I have a bunch of variables that are multiplied together or divided, in this case, they're multiplied again, then I have to add these respective prads, right? So basically what you're doing is just adding the prad for diameter three times. So this is going to be the prad for diameter plus the prad for diameter plus the prad for diameter. And of course that, you can simplify it, just equals three times the prad for diameter. Okay, and that will be the prad for your volume of the basketball. Okay, and then so after you're done calculating prad for volume, Then I tell you, suppose the accepted value for the volume of a regulation basketball is given as 7130, so 7,130 centimeters cubed. So that's like the accepted gold standard value, right, for the volume of basketball. I want you to compare your experimental value, so whatever you computed here for your volume, compare that to the accepted value of 7130. How do you do that? You're going to compute the percent experimental error, right? When you compare your value, your experimental value to the gold standard. So where it says experimental value here for the basketball, that's the volume that you calculated, right? So that'll go in here in the table. And then you're going to use those two values to compute the percent experimental error. So to remind you how to do that, again, let me jump over to the tablet. Okay, so remember, in general, the percent experimental error is equal to the experimental value minus the accepted. And often I call the accepted predicted, sometimes theoretical, right? It has different names. So accepted, theoretical, it's sort of like the gold standard value. But then you want to make sure that's non-negative, right? So we're going to take the absolute value of that. And then the key is I have to divide by the accepted value. And then if I multiply by 100, that will convert that ratio into a percent, right? So it's experimental minus accepted divided by the accepted or predicted or gold standard times 100. So in your case, you're going to use the experimental volume. I'll just write as VEXP minus the accepted that I gave you, that value that I gave you, divided by the accepted value times 100. Okay, and again, the answer will be as a percentage. And the lower the better, right? In this case, remember, you could actually have 0% if you got exactly the same as the accepted value. Okay. Okay, and then the last part of this first lab was just giving you some practice on graphing. So first of all, using everything you learned from the good graphing techniques handout and from those video lecture and the good graphing techniques, and then getting a little practice using Pascal Capstone to actually do your graphs, right? To plot your graphs. So in this first case, you're told that you have some position versus time data that was collected from a cart that's moving on a horizontal air track. So the time values are given here in this column, and then the position of the cart is in the second column here. And I want you to plot position versus time. So position would be on the y-axis and time is on the x-axis. And then based on the shape of your graph, what type of curve fit do you think you should use? And then perform that fit. And then I want you to compute or actually just record because the computer will give it to you, record the slope of that graph. So actually, because I'm asking for the slope, we know that this should hopefully be a linear fit, right? The curve fit should be linear in this case. Okay, actually, I'll jump on Pascal Capstone to show you a little bit of how to do this in a second. Let me go over the last question here. So this is basically the same thing. So again, we have some position versus time data, but now it turns out that this data has sort of like a quadratic function in terms of time. So when you do the curve fit for this data, it should be a quadratic fit. You should see this nice like parabola when you perform this particular fit. Okay, so again, it's just practice on using Pascal Capstone and doing some of these graphs. Okay, let me show you how to use Pascal Capstone. Okay, so when you start up Pascal Capstone, you're going to get this introductory menu here. And what I would do, there's several ways of getting into each option that we want, but what I would do is just click on Classic Templates. And then for this class, we're almost always going to use this upper left icon right here with the one with the table and the graph in it. So I'm going to click on that. Okay, so to put in my data here, I want this to be time. So I'm going to go to select measurement, create new, user enter data. And then normally I would just name this time. However, there's a problem. It's like a reserved keyword for this particular program, and it'll give us some error if we just try calling it time. So just call it like time two or time underscore. Time two will be fine. Just something other than time, and you'll be fine. Hit tab or enter. And then for the units, we want time to be in seconds. Okay. And then for the second column, create new, user enter data. I want it to be position, and then I want the units to be centimeters. Okay, let me just make up some data here. Let's say my times are 1, 2, or 0, 1, 2, 3, 4, 5 seconds. And then my position is, say, I don't know, 0, 11.2, 19.5, 31.2, 39.0, 51.0. Let's say those are my values. Okay, so to plot these now, remember I want to plot time on the x-axis. So I simply go down to the x-axis where it says select measurement. I'm going to choose time. Go to the y-axis. I'm going to choose what I want to plot, which is position. Now it does the one thing that I don't want it to do at the beginning. Let me move this out of the way as well. Actually, sometimes if you click on this, it doesn't highlight it anymore. So you have to click on it again to highlight it again. So the one thing that we don't want it to do is just do these line connections to all the data points because we want to do a curve of best fit. So the first of all, to get rid of those line connections, if you hover over a data point and you right click on your mouse, you should be able to uncheck show connecting lines. By the way, sometimes if you have a Mac, you have to hold the control key down when you right click, and then you should get that menu and uncheck connecting lines. Okay, actually, let's give it a title. So remember, the easiest title to give a graph is just the y variable versus the x. So I could just call this position versus time. And then for the fit, well, in this case, it's pretty linear, right? From the data I made up, it looks pretty linear. So I'm going to go to the fit icon. Again, you have to be careful here. If you, to the left of the arrow here, this will turn the fit on and off, right? So that's off. Make sure it's on. And then use the arrow to choose what you want to do for your fit, which we want a linear fit. So I'll choose linear. Click on the graph again. And then it does the linear fit, right? The line of best fit. And it gives you a bunch of information. The important thing in this case is going to be the slope. So with my made up data, my slope is around 10 centimeters per second. Don't worry about these error terms here. So this is going to be an important, the slope. And in many labs, we will want to record that slope value. They also give you the y-intercept, right? The b, and then the correlation coefficient. So it's a good fit, right? It's a really high correlation coefficient. It's nearly 1. Okay, the last thing you'd want to do with this data is potentially save it, right? So you can put it in a group lab report. So to do that, if you hover over the border here, so it's highlighted, the blue rectangular border, right click, and if you go to copy display, then it copies it to the clipboard and you can paste it into whatever program you guys are using to share when you work on your group lab reports. Typically it's Google Docs, right? Or maybe you're sharing a Word document. Okay, so really that's all there is to graphing. If we want to graph the second one, let's say we want to graph time position versus time again, but now we want it to be a quadratic type function. Let me see. Okay, so again, if we want to plot a new graph, say another position versus time, but this one will be a quadratic function, you could just start this over again, or if you want to just add another column here, this left little icon here will allow you to add another column. So I'll go to select measurement, create new, user enter data. Let me give it a new name like position 2. And then again, I'll do centimeters. And then let's say these values are 0. Trying to think of something that'll be approximately quadratic. Um, let's say this is maybe 1.1. and then 3.9, and then 9.5, 16.0, and then 25.8. Okay, something like that. So again, I can, if you want, you can do the same plot on here. I can choose time. I already have it on the X. I can go to the Y and change that to position 2. Now notice, sometimes it rescales everything. It may do that correctly for you. If not, you can always use this icon right here to the left to rescale it. So it just zooms everything in correctly. We don't want this linear fit, so I'm just going to click on it to get rid of it. For the title, I should probably call this position 2, right? So position 2 versus time. And then again, I don't want these line connections here. So to get rid of them, I'm going to hover over data point, right click, show connecting lines, right, to get rid of them. And now for the fit, I want it to be a quadratic fit, right? That'll give me a nice parabola here. So if I click on quadratic, so that does a nice quadratic fit. Okay, and it gives you a bunch of information. Actually, it'll give you these coefficients here for the equation that gives you the actual best fit through all your data. In most cases, we won't worry too much about this when we do quadratic fits. For linear, it's important to get the slope, but for quadratic fits, I just want a nice, parabolic fit to the data. And then if you wanted to save this again, you would hover over the data, over the border here, the rectangular border, right click, go to copy display, and then paste it into your Google Docs. Okay, that's it. Just practicing a little bit. Actually, this whole first lab is just practice. I'm not going to have you write up this first lab. It'll be the second lab that we're going to actually write up. So this one is just practice. Thanks.